We're now going to look at our joint orientations. I've attached the Visualize Rig node to the skeleton. This will allow us to look at the joint orientations. If we pay careful attention to the rig, we'll see that we've got numerous problems. We can try to make these more clear by using the GNOME on display. However, I'm actually not going to be using the rig visualization node, so I'll delete the node, and instead I'm going to be using the information which is already on the skeleton itself. I'll bring up the information for the node. I'll then click on Transform. This will activate the visualizations for the display. I can right click on the visualization icon to bring up the visualizations menu. I'll then click on the pencil icon to edit the transforms. In this case, I'll change the length scale to be 0.1. This will make it easier to see what's going on with the transform visualizations, and I can make things a little bit more clear by hiding the mesh as well. My visualizations aren't refreshing properly. I'll turn them on and off again to force an update. We have some fundamental problems with the orientations, and one of the easiest places to see the problems is with the legs. If we look at the x-axis on the joints and compare that with the root, we'll see that they're completely different. In fact, the y-axis on the joints is closer to the x-axis on the root. If we line up the points of the leg, the problems become even more obvious. None of the orientations match, and they also are not lying along the plane of the leg. This is also something which happens consistently with every single one of the legs. The reason for this is that the default orientations are calculated with an average. This will provide a workable result in most circumstances, but it does not provide a good result. I will be working through this rig systematically to create custom orientations. We'll start with the Delete Joints node, and I'll make a duplicate of this node. These will be connected to the skeleton. For the first of these nodes, I'm going to select all the joints that lie along the center of the rig. These will be the body, the head, and the abdomen. These are all points which should rest along 0 in the x-axis. We'll then select Delete Non-Selected. I've now separated the center of the rig. If we look at the front view, we'll see that we've got problems that we need to fix. But before we deal with that, I'll set up the second Delete Joints node. Once again, we'll select the center of the rig, and in this case we'll leave it on Delete Selected, and this will separate the legs from the body. At this point we can try to add the Reorient Joints node and see if we get better results. We do get different results, however they're not necessarily much better than what we had before. Once again, this is trying to get a very good result for the entire rig, and this result has to be based off an average, so there are fundamental problems which you get from that. I'll attach the Reorient Joints node to the first Delete node. If we look at the front view, we'll see that the rotations which were okay are now actually all over the place. This is one of the dangers of using the skeleton node. When the tweak tool is on, it is very easy to move points out of alignment, and all of these joints are out of alignment. These points should all be resting at 0 on the x-axis. This is not easy to fix using the skeleton node, so we'll use other methods. So I'll want to fix these, and I'll start by getting an attribute wrangle node. I'll connect this node after the Delete Joints node, and we'll just be aligning these points along the x-axis. The correction amount is very small, so we shouldn't have to worry about it causing problems. We'll be working on the point position attribute, and we'll use the set function. The first value, which will be our x, will be set to 0. We'll get our second value from the point position itself, and this will be set with its own y value. This will be done by specifying the index 1. The z value will also be set from the point z value. This will be done using the index 2. And this will mean all our points are now centered on the x-axis. And we've now zeroed out the position, but if we look at the Reorient Joints node, we'll see that our results are actually even worse now. This comes from the fact that all these points are on a single axis now. And no matter how you try and generalize the calculation of the transforms, you are always going to have problems when the points are lying along a specific axis. This can be easily illustrated in this case. If I use a unit vector in y as a reference vector, I get much better orientations. It is possible to mitigate some of this using target groups, but even then I think it is actually easier to create custom orientations. I'll now split things up further to make the orientations easier to deal with. I'll get a delete joints node, and I'll start with the center of gravity and the root. We'll also set this node to delete non-selected. In this case, I'll want to double check the point position. Both of these points should lie at 0 on both the x-axis and the z-axis. I will then get a wrangle node. For these 2 points, the orientation will be very straightforward. First, I want to create 3 directions, and each of these directions will be a vector. We'll start with the x direction, and this will be set to 1, 0, 0. We can use the resample joints node to illustrate what we are actually looking for. In this case, we'll want the z direction to point along the length of the bone, which also means that the y direction will not be facing upwards. So we'll set the y direction with vector y direction. We'll use the set function, and this will be 0, 0, negative 1. In this case, the z direction will be pointing straight up for both of these points. So this will be vector z direction. We'll use the set function, and we'll set it with 0, 1, 0. We've created our vectors, and we'll now need to set our transformation matrix with these vectors. We will need to specify that our attribute is a 3 by 3 matrix. We'll do this with the number 3, which will precede our attribute. And in this case, the attribute we want to update is the transform. This is generated by the skeleton node and is used to define the rotation of a joint. It can also be generated using a reorient joint node or a rig doctor node. This matrix can be set with 3 vectors. Each of these vectors will represent an axis of the transform. For a rotation matrix, all of these vectors should be a unit length of 1, and these vectors should all be orthogonal, which means that they should all be perpendicular to each other. So in this case, these vectors do not need to be normalized, but I will always do this as a matter of course. So the first vector will be normalize x direction. Then we'll set normalize y direction, and the third vector will be normalize z direction. We should now see that my transforms have changed, and if you want to see what we've actually set, we can go to the geometry spreadsheet, and there will be a set of values over here under transform, and these will represent the transformation matrix. We now have a consistent orientation for both of these joints. So this sets up the root and the center of gravity. Next we'll need to work on the head and the abdomen. So I'll duplicate the delete joints in the attribute wrangle node. I'll then change the selected groups to be the head root and the head effector. Currently it looks okay, but we actually need the z-axis to point along the bone. If we plug this into the reorient joints node, we'll get the correct behavior for the z-axis. So we'll want something which is like this, but without the awkward rotation. We can now start working on the attribute wrangle node. This current setup will not work, but we will use it as the base for our orientations. I'll start by setting the x, y, and z to be default orientations, so they'll basically form an identity matrix. I'll then comment out the line where we set the transform. We'll still use this line, but I do not want to try and compile it at the moment. We will then add functionality that is not native to Vex yet, and we'll add this with an include command. Anybody who is familiar with either C or C++ will recognize this. Hash include, then we have quotation marks, and within these we'll have KineFX.h. This will give me functionality, In this case, it will allow me to find the parent or the child of a current joint. So for these points, we're going to work on each point individually, and I'll be specifying each point by name. So we'll have the conditional, if, then we'll be looking for the name. We'll get this with @name. We'll be getting the name using the suffix, so we'll look for points from the end. To specify a point, we're going to use an index, which uses 2 square braces, and we can specify a specific index using a number. If I want to start looking for the index from the back of the name, I'll make this a negative number, and that is what we'll do in this case by setting this to -3. This will give me the third letter from the end of the name. I can then specify that this will continue towards the end of the name by placing a colon. This will give me the last 3 letters of the name. I will then check that this is not equal to EFF. We currently only have 2 points, so this will specify that this is the root. For these points, I'll be using an up vector to help generate the transform. So I'll create a variable to store this in. This will be a vector, and it will be called up. By default, I'll initialize this to be a 0 vector. In this case, the up vector will be a unit vector in x. So I'll set this using up is equal to our x direction. I'll then need to get the point position for my first point. I'll store this in a vector, and I'll call this vector point 0. I'll then get my point position. We'll do this using the function point. We'll be getting our point from input 0. The attribute we want is the point position, and this is defined with p. We'll then need the specific point we're looking at, and that will be at pt_num for the current point. The next thing I want is the point position of the first child of this point. This will again be stored in a vector, and I'll call this point 1. We'll use the point function again. The input will be 0, the attribute will be p, and we'll need to get the child of the current point. We can do this using a function getChildren. The input will be 0, and this will take the attribute at pt_num for the current point. GetChildren returns an array, however we only want 1 point. So to specify a single point, we're going to use 2 square braces, and we're going to use the index 0. This will give you the first child of a point, and in this case I only have 1 child. As we have the z direction pointing down the length of the bone, we'll start by setting the z direction. And we'll do this by subtracting point 0 from point 1. We want to be able to visualize this value. To do this, I'm going to create an attribute. This will be a vector attribute, and its name will be z. As with the earlier nodes, we want these parameters to be normalized, so I'll set this with normalize z direction. I have an error here. I forgot to set the type of up to be a vector. I can select my wrangle node and look at the information for this node. I should now have an attribute called z. I'll click on this to enable the visualizations. I can open the contextual menu for my visualizations, and I now have my z attribute showing. I'll hide all the other attributes. My x attribute is currently displaying as a color. To make it more usable, I'm going to edit the visualizations. I'll change the type from color to marker. The style will then be changed to vector. As this is a z-axis, I'll set the color to be blue, and I can set the length scale to be 0.1. I have my z vector, and it is pointing down the axis of the bone, so this is exactly what I want. I will now calculate the y vector, and I'll do this using the cross product of the up direction and the z direction. We duplicate the visualizations twice so we can have all 3 directions. We'll then rename them so we have an x direction, a y direction, and a z direction. I will need to activate the y and x directions. Once again, I'll do this using the information for the wrangle node. I'll click on the x attribute and the y attribute. I'll then set them via our visualizations. I'll start with the x attribute. The type should be marker. The style will be vector. I'll set the image scale to 0.1 and I'll set the color to be red. Next I'll do the Y direction. This will be a marker. It will be a vector. The length scale will be 0.1 and I'll make this green. I have my transform set up, and in this case I probably do not have to calculate the x-axis, but I will force this in any case. I'll set my x direction by taking the cross product of my z direction and my y direction. In this case the x direction is facing the wrong way, so I'll swap around the y direction and the z direction. I now have my first point set, and it seems like we have the second point set. However, in this case I'm going to explicitly set the second point. I have two reasons for doing this. The first is it serves as a useful example. The second is I'm going to have to do this in any case when we come to the legs. So I'll duplicate the first conditional and all its logic, and we'll change the conditional itself. We'll now check if the name ends with a vector. We are now setting the last point, but we're getting incorrect values, so we'll need to adjust how this point is being calculated. I'll comment out where I set the x and the y direction, just so that we can focus on one thing at a time. One of the things with working with the last point is this point has no children, so we'll need to change point 2, and in this case we'll be looking for the parent. To find the parent point, we'll use a function which is called getParent. The first argument of this function will be the input, and that will be 0. In this case we are only using the first input. The second argument will be @ptnum for the current point. Unlike the getChildren function, this function returns a single integer, so we no longer need to state the index at the end of the function. I'm now getting the z vector, but I want it to be facing in the opposite direction. There are two ways I can do this. I can either swap around the points in the equation, or in this case we'll just group those with parentheses and multiply them by -1. I then want to set my y direction, and we do not need to change it because it is working, and the same applies for the x direction. We now have proper transformations for the head joints, and next we'll work on the abdomen. I'll duplicate the delete joints node and the attribute wrangle node for the head, and we'll use these for the abdomen. In the delete joints node, I'll replace the group. The new group will be for the abdomen root and the abdomen effector. And we now have transforms for the abdomen. These transforms are perfectly fine. I could reverse the up vector to make the y-axis point upwards, but I will leave them as they are for the moment. So I now have working transforms for my entire body, and we'll need to work on the legs. I'll duplicate the attribute wrangle again, and I'll connect this to the delete joints node for the legs. We can now start working on the legs properly, and the legs are far more complicated than the previous joints. The specific approach we're taking here will only work properly because the legs are aligned on a plane. To get some more clarity, we can take a look at the names. With all of the legs, the first point has the suffix root, and the final point has the suffix effector. In the wrangle node, we are already isolating the first point and the last point. However, the conditional for the first point will no longer work as expected, and we'll need to calculate all the points between the first and last points. The way this is going to work is we're going to work with groups of 3 points. So for the first point, we'll have the first point and its first 2 children, and we'll use these 3 points to calculate the space of the first joint. For the joints in between the first and the last joint, we'll calculate its transformation using its parent point and its child point. For the last point, we'll calculate the transforms using the point itself and its 2 preceding points. I want to keep most of the script, but I want to go through everything in order at the same time. So I'm just going to comment out everything so I can work through things step by step. I'll then move my visualizations into the first conditional. We'll now look at what we're generating. We're generating transforms for each of the points except the final point, and these are all identity transforms. So we'll have to change the conditional to isolate the first point. We'll do this by looking for the root suffix So we'll change the conditional to if attribute name, and we'll look for the last 4 points, and we'll check if these are equal to root. Then, in order to keep things neater, I'm going to calculate the first child of my point. This will be an integer, and I'll call it child. We'll get it using the getChildren function. The input will be 0, and we'll get the value of the current point. To do this, we'll use the attribute ptnum. Once again, the getChildren function produces an array, and we only want the first child, so I'll specify the index 0 at the end of the array. There'll be no change to point 0, but we'll need to change point 2. We will now be getting the point position attribute using our child variable. I will then need to get my third point, vector point 2, and we'll set this using the point function. We'll be using the first input, or input 0. We'll be looking for the point position, and we'll get this position using the child of our child. We'll do this with the getChildren function. This will use input 0, and the second argument will be our child. We'll select the first child using index 0. We now have 3 points, and I can start working on the commented out section. We'll start with the Z direction. There should be no change required here. I'll isolate the visualization, and it is working as I expect it to. The next thing we'll need to find is our X direction. We're no longer going to be setting the X direction with an up vector. Instead, we're going to get it from our points. So the X direction will be set with the cross product. The first argument will be 0.1 minus 0.0. The second argument will be 0.2 minus 0.0. This will give us a vector which is perpendicular to the plane of these 3 points. And this is what we should see when I activate the visualizations again. We can then check if it is correct using the right-hand rule. This is because Houdini uses a right-hand coordinate system. With the right-hand rule, you usually use the thumb as the X direction, the index finger as the Y direction, and the middle finger as the Z direction. You then line these up with the axes to see if they're facing in the correct direction. I can then remove the comments for my Y direction. I'll need to change the equation though. This should now be the cross product of the Z direction and the X direction. I should now have the correct transformation for my points. I can delete the variable for the up vector as I'm not currently using it. I can now compare these orientations with those of my reorient joints node. These orientations are very different. In fact, the reorient joints node is actually calculating the orientations in the opposite direction from what you would expect. I will then want this to apply to all the intermediate joints. I'll duplicate this conditional. We'll change this conditional and we'll check if the suffix is no longer equal to root. We'll also want to make sure that this is not equal to a vector. This way we'll exclude both the first point and the last point from this calculation. We are now setting transforms on these points, but there are a couple of things which we'll need to fix. It may look like it's correct, but we're actually not setting the vectors from the correct points. I can delete this child declaration, and we can now change the calculation of the point positions. The first point will be the parent of the current point. So instead of using ptnum, we will use getParent. The input will be 0. And we'll get this from our current point, which is at ptnum. The second point will be our current point. So instead of using child as the point, we'll use at ptnum. The third point will be the child of our current point. We'll once again use getChildren, but this will get the child of our current point, so this will be at ptnum. And we'll need to get the first child, so we'll use index 0. I correct my mistake where I forgot to add input 0 to the getParent function. We now have updated vectors. The Z direction is no longer pointing down the length of the bone, so we'll start by recalculating the Z direction. This will now be set relative to the second point instead of the first point, so it will be 0.2 minus 0.1. We will also have to update the cross product. The first value will be 0.2 minus 0.1, and the second value will be 0.0 minus 0.1. We should now have the correct orientation on our intermediate joints. If we line up the points, we should see that our orientations are orthogonal to the points. We can now move the visualizations out of this conditional. The roots transform should match the intermediate joints transforms, and all of them should be orthogonal to the plane of the leg. I'll now be working on the final joint. I'll copy my visualizations and paste them within this conditional, and I can start removing the comments. The conditional will remain unchanged. I'm working with the last point, so I want to calculate the previous two joints. Here the first point will remain unchanged. I will once again want to find the first parent joint. It will be an integer, and I'll call the variable parent. And we'll get this with the getParent function. The input will be 0, and we'll get the parent of the current point. We can then get the second point using this variable instead of the function, and we'll need to get the third point. This will be a vector. It will be called point 2, and we'll get its point position using the point function. The first argument will be input 0, then we'll specify the point position, or p, and then we'll get the parent of the parent. This will use the getParent function. It will use input 0, and the second argument will be parent. We can then uncomment the z direction. This point should be correct already, as we already negated it in the previous version of the script. Next comes the x direction, and we'll specify this using the cross product. The first argument will be 0.1 minus 0.0. This will be followed by 0.2 minus 0.0. I can then set my y direction to be the cross product of my z direction and my x direction. In order to see the visualizations for the transforms, I'll need to move them out of this conditional. The transforms for the final point are now visible, and unfortunately they're not matching the previous transforms. I'll need to swap the arguments for the cross product for my x direction. So the first argument will be 0.2 minus 0.0, and the second argument will be 0.1 minus 0.0. We should now have transforms that are perpendicular to the legs. I can now remove the visualizations, and we can make sure that we're setting the transform. I can delete the extra visualizations because now we only need the transforms. I will remove the visualization attributes from all of the angles and make sure we're setting the transforms in them all. We've completed the transforms and can now reconnect all the limbs. I'll select all the attribute wrangle nodes, and I'll drag out a network holding Alt. We'll get a reparent joints node, and we'll connect it to the merge node. I'll add an operation. The first parent will be the center of gravity. This will be the parent of my head root and my abdomen root. I'll add a second operation. The parent will be the abdomen root, and this will be the parent of all the leg roots. We now have a completed skeleton with much better transformations. There are, however, still a couple of things which I need to do to finish the skeleton, and we'll do them in the next video.